شرفنا يا دكتور، شرفنا، ربنا يخليك. انا سمعت هنا. تمام كده، ماشي، شكرا جزيلا. طيب خلاص نبدا المحاضره. almost 1 يعني. ماشي. انا تاني احب اشكر جدا دكتور عمرو ودكتور تامر ان هم they made it happen. الحقيقه الواحد سعيد جدا، انا اول مره ازور جامعه النيل ويعني اتشرفت جدا جدا جدا. انا هتكلم على يعني few topics، ومعلش ساعات ايه ان اجزاء من التوك دي اديتها يعني في الجامعه عندنا كذا مره، فغالبا حافظ اجزاء معينه بالانجليزي، فهتلاقيني ساعات اشرح كده شويه. اتس اوكي يعني، مش مساله حاجه. طيب، فاول جزء عن الاستابيليتي اوف انسكت فلايت ده. اوبس يس، حاضر ماشي. بس هو ليه ده ما اشتغلش؟ I need it to work. Yeah, video. This is weird. لا انا عندي شويه فيديوهات كول، فلازم الفيديوهات تشتغل، مش ينفع ما تشتغلش. This is weird. ليه ما بيشتغلش؟ It's okay. كده يشتغل. What's happening? Not now. So ده الغريب انه على اللابتوب بتاعي، فهو المفروض يشتغل. اوكي yeah. Here you go. ده حشرة اسمها هاك موث. Basically يعني this is a slow motion video. Basically moves its wings back and forth. بس ببساطة شديدة، بس ده slow motion video. المفروض الحشرات بتتحرك بتعمل فلابنج بسرعة أكبر بكتير. فالحقيقة طيران الحشرات كان puzzling للبيولوجيستس وايروديناميسيستس scientists in general for like a century. ببساطة لأن معادلة البالانس المفروض إن أنا generate lift يبالانس الويت. طبعا احنا عارفين الدنسيتي بتاع الهواء، عارفين how fast the insect moves its wings, how large its wing area, and how much does it weigh. فبالتالي اقدر اجيب من هنا ال CL required for balance ببساطه شديده جدا. On the other hand, I know the maximum achievable CL using conventional aerodynamics. This is a function of Reynolds number. Insects are operating here in the ultra low Reynolds number regime. فطبعا quite low CL max. Usually CL required for balance is about 2 to 3 times the maximum achievable lift coefficient using conventional aerodynamics. فعندنا papers, countless papers, they concluded by saying something like insect flight is impossible using conventional aerodynamics. There must be unconventional lift mechanisms. And it wasn't until recently, actually, يعني هنا 1996, paper in Nature by Ellington and his co-workers at Cambridge, and another paper in 1999 in Science by Dickinson and his group at Caltech. They figured out the main unconventional lift mechanism that made insect flight possible, which is a leading edge vortex. A leading edge vortex that augments the usual bound vortex over the wing, so it increases the lift in a usual sense. Once you figure out how insects lift their weight off the ground, the immediate question is, how do they stabilize their attitude, their flight? Do they employ feedback control? Is it naturally stable? This is the question that we recently answered, and this is one of the main topics of today. So this is a flapping animal in the longitudinal plane. So rigid body in a plane, 3 degrees of freedom. Use the forward speed of the body, W normal speed of the body, Q pitching angular velocity, theta is the pitching angle. X, Z, and M are aerodynamic loads and pitching moment. If you neglect wing flexibility and wing inertia, you happily recover the exact same set of equations as conventional airplanes. ده اللي احنا بندرسه في الاندرجراد سنه رابعه. Standard. So this is why we're happy, because this set of equations has been studied for decades. We have huge legacy to exploit. Gravitational aerodynamic loads, gravitational and inertial loads, I'm sorry, and here are the aerodynamic loads. But here, unlike conventional airplanes, these aerodynamic loads are essentially time varying. انتوا شفتوا في الفيديو in the first slide in the insect accelerates its wings and then decelerates because it has to come to a complete stop and changes the angle of attack throughout the cycle. So these aerodynamic loads are essentially time varying. If I write this system in an abstract form, it will be it will have an explicit time dependence. So now it's not only nonlinear but time varying. So we're not happy anymore because this time variation is tricky. So even for linear systems, x dot equals ax. Everybody in this room knows by heart that if the A matrix has eigenvalues in the left half plane, the system is exponentially stable. But x dot equals A of t times x. If all the eigenvalues lie in the left half plane for all times, this does not guarantee stability. We have a counterexample. So time variation is tricky. Okay, here is our system again. And we can write down our aerodynamic loads linear in the states, linear in the motion variable. So this is aerodynamic loads due to flapping motion only of the wing. And this is interaction with the body motion through just regular stability derivatives. These are time varying stability derivatives. Ignore all this mess, but just observe that we used two symbols, t and tau, to denote the independent time variable. And this is to stress the fact that we do have two time scales, a fast time scale for the flapping motion and the associated aerodynamic loads, and a slow time scale of the body motion. And to give you an idea, على ال two time scales دول, you as a human being with your bare human eye تقدر ان انت تtrack the motion of one insect from one point in the space to another, right? It's easy. But you cannot track the motion of their wings. They move their wings too fast. And again, I'm talking about insects, not wings. For we definitely have two time scales. For one of the slowest flapping insect, the hawk moth, the ratio between the flapping frequency to the natural frequency of flight dynamics is about 30. فتحاول تخيل دي كده عندك جسم بتهزه بفورس varying. Its frequency, speed of variation, is 30 times its natural frequency. Most likely, the body will not feel this oscillation, will only feel the average values of the aerodynamic loads, of the forces. So this actually invokes averaging, which was adopted first by biologists. So let's average out over the fast time scale, over the tau time scale. Anything over bar here indicates average it, cycle average it. So there is no explicit time dependence. It's still nonlinear, but that's fine. We can always linearize about an equilibrium, say hovering. We get a system matrix and check the eigenvalues. And we have like tens of papers, including mine, that did this kind of analysis, finding a complex conjugate pair in the right half plane, indicating instability. So it's kind of fact among flapping flight dynamics community that insects are unstable at hovering. And everything made sense at the time. Why? Because if you look at the eigenvectors associated with this pair of eigenvalues, you will find that it's mainly associated with pitching motion. So instability is mainly due to the pitching motion. Why? Because we don't have a pitch stiffness. We don't have CM alpha kind of term, if you're familiar with flight mechanics terms. And if you ask, okay, so ايه كان السورس بتاع CM alpha للconventional airplanes? Well, it's horizontal tails, right? These insects, they don't have horizontal tails. And even if they do, horizontal tail will not be effective unless you have a forward flight. You have a forward speed. If at hovering, horizontal tail will not provide pitch stiffness. And this is why helicopters also suffer from the same issue. So to an aeronautical engineer, an insect hovering over a flower is very similar to a helicopter hovering in place, and both of them are unstable. Everything made sense at the time, except we as engineers should have a mathematical justification of what we're doing. We need to have a stability certificate. يعني ما ينفعش تبقى بالintuition كده. Okay, we dig a bit in the mathematical theory of time periodic systems. Here is an averaging theorem. الام هنا بتريح جدا. X dot F هنا periodic in time. Epsilon is a small parameter. Okay, simply average over the cycle. And so now you turn a time periodic system into a time invariant system. Good. Which means if you had a periodic orbit representing equilibrium here, now it reduces to a fixed point. Good. Of course, analyzing the stability of a fixed point for a time invariant system is much, much easier than analyzing the stability for periodic orbit for time periodic system. And here is the mathematical statement of the theorem. If this guy is for a small enough epsilon, if this guy is stable, that guy is also stable. So for a small enough epsilon, stability of the fixed point implies stability of the periodic orbit. A very powerful theorem that may seem to support the work of biologists, because you got to analyze the stability of an easy system and conclude the stability of a hard system. Very good. Except it says for a small enough epsilon. What's the epsilon here? Epsilon actually in this problem goes by the reciprocal of the flapping frequency. So for high enough flapping frequency, hopefully epsilon is small enough for direct averaging to work. And this is the main intuition behind averaging in the first place, right? Again, how small is small enough and how high is high enough. Actually, أنا ما لقيتش more expressive statement than this statement in the book by Sanders and Verhelst, which I call the Bible of averaging. They say, to many physicists and astronomers, averaging seems to be such a natural procedure that they do not even bother to justify the process. However, it is precisely the fact that averaging seems so natural that obscures the pitfalls and restrictions of the method. We need to have a more rigorous mathematical analysis tool that either supports or refutes the work of biologists. And if you dig a bit more, you always find Russians behind the scene, right? So this is two Russian mathematicians, Agrachev and Gamgrelidze. Two Russian mathematicians, they wrote this paper in the honor of the 70th birthday of the great Russian mathematician, Lev Semyonovich Pontryagin. Pontryagin, the founder of optimal control branch, Pontryagin maximum principle. كانوا الستودنتس بتوعه فكتبوا في عيد ميلاده ال70 بدل ما يجيبوا تورتايه وبتاع كتبوا له البيبر دي. البيبر دي عملوا فيها كالكولس جديد اسمه chronological calculus. Calculus دوت is useful for time varying systems. Okay, nice. Later on, Sarychev, another Russian mathematician, Patricio Vela, as a colleague, he's at Georgia Tech. This was his PhD dissertation at Caltech. They used these tools to develop what they call complete averaging. So if you have a system on this form, F is periodic in time, epsilon is not necessarily small in this case. Well, its complete average dynamics is not only average over the cycle. It's actually an infinite series. The first term is the average over the cycle. The second term is the average of a bracket between f and its integral. The bracket is the Lie bracket, so that's okay because now I can compute as many lambdas as I want analytically. It's just integration and differentiation. Very good. So you can do analytical stuff. And here is the mathematical statement of the theorem. If the series converges, then if this guy is stable, that guy is stable, irrespective of epsilon. Stability of the fixed point implies stability of the periodic orbit, irrespective of epsilon. This is why they call it complete averaging. There is no approximation. If epsilon is small enough so that epsilon square is negligible, we can truncate after the first term and recover direct averaging. If not, we go higher and higher until we capture the required accuracy. This is what we did. We used several methods because عشان تقول حاجه عكس الكوميونتي محتاج تطمن نفسك يعني. فلوكي theorem, if some of you knows it, I mean it's just a numerical tool, so we can't have any physical insight. Black box, and it's applicable to linear system, linear time periodic. We also used method of multiple scales, analytical, so it gives you some insight, but also in the linearized version. And we used second order averaging or higher order averaging that I just presented analytically on the full nonlinear time varying system. And here are the results, eigenvalues. So red cross here is for first order averaging. You can see the instability. Green ones using method of multiple scales, all lie in the left half plane. Pink ones using second order averaging, all lie in the left half plane. Blue ones using Floquet, all lie in the left half plane. The system is indeed stabilized. On the average, the system is unstable, but these high frequency vibrations of zero mean that they are typically neglected when you do averaging. They induce stabilizing action. Okay, so the interesting point is, what's exactly going on? So because we have an analytical tool, now we can go indulge and see what's going on. So this is the system matrix of first order averaging for the hawk moth at hovering, and this is second order averaging. You can compare term by term to see what's going on. For example, the first term here representing damping in the forward direction decreased a little bit, damping in the normal direction decreased a little bit, pitch damping increased a little bit. But of particular importance here, look at this term, it was actually zero. So it's created solely due to these vibrations. Let's interpret this term. So let's recall the system structure. This is third row and fourth column. So third row is Q dot. Fourth column is theta. So this reads as Q dot or theta double dot, pitching acceleration or pitching moment due to an angle with a restoring sign. So a moment due to an angle or a force due to displacement, this is a spring action. So the system on the average is unstable, but if it's perturbed a little bit from equilibrium, these high frequency vibrations, again of zero mean that are typically neglected when you do averaging, they induce a restoring pitching moment that is proportional to theta in the form of a spring. And this is not the first time to see a vibrationally induced spring. Here is the textbook classical example, the inverted pendulum, and we actually built this in the lab. It's an unstable system. If you leave it, it falls down. But if you vibrate it up and down, look at the behavior. Look at how it behaves. So we're going to do a disturbance now on the inverted pendulum. Look at how it restores to its equilibrium, exactly as if we have a torsional spring. And I swear we don't have a torsional spring. It's just vibration up and down. And the beauty about the math behind is that when you do the higher order averaging, this is the equation that you get. It's actually as if you have a spring action, and you can relate this spring constant to the amplitude and frequency of the motion. Fine, let's demonstrate it on a robotic insect. I mean, robotic flapping air vehicle, or whatever you want to call it. It's just a flapping wing kind of thing. So here we have like a pendulum, and we have the flapping thing at the end. Why we're doing this? Because this is just a 1 degree of freedom for the body. Why we're doing this? Because now I'm allowing for multiple equilibrium positions. If I'm flapping slowly, I will not be generating enough lift, so I'll be down here. If I'm flapping faster, and I will generate more lift, so I'll be up there. So I can operate at multiple flapping frequencies. Why is that? Because vibrational stabilization is only evident beyond a certain threshold of flapping frequency. So we need to study this threshold. Okay, fine. This is just 1 degree of freedom. Now we need to add the other degree of freedom that is the main source of instability, the pitching one. So we're going to change this fixation to a hinge. Here is a 2 degree of freedom one. We're flapping relatively slowly because we're down here, and you can see that the system is crazy unstable. Just increase the voltage of the motor, increase the flapping frequency, go up, and here is the response. It's naturally stable, and even if you push it, and this is a hard push, by the way, it's 50 degrees disturbance, 50. It's very robust. You push it all the way, it comes back. It's very robust. We said, okay, let's do one more thing. Let's replace the flapping mechanism by a propeller. So the wings are there stationary now. It's not the main source of thrust. We have a propeller. And we match inertia and weight and everything that we could. Then the only difference between, or the main difference between the two systems is that the propeller revolves at a constant angular velocity, producing a constant thrust force. So the dynamics are time invariant. There is no room for vibrational stabilization here. And if you touch it, it's just unstable. And this is the behavior at any equilibrium position. Actually, it was quite hard to attain this equilibrium because it's unstable. So this gives us an idea that the main stability observed here was mainly due to the oscillatory nature of the driving aerodynamic force. If it's constant aerodynamic force, we don't get the same thing. And finally, we said, okay, let's see this on a real animal in action. So we called our biology expert, Professor Taha at the University of North Carolina. He had this nice experiment. He shoots moth with a plastic projectile. So بيعذب الحشرة يعني. وعنده high speed cameras فيقدر يدينا the motion of the body and wing. فده اللي بيديه لنا. احنا هو بيعمل الاكسبيرمنت ويدينا داتا بتاع body motion and wing flapping motion. طبعا احنا body motion ده نقدر we can pass it to a low pass filter to extract the slowly varying component, the average it, and within cycle variations of zero mean, and pass it to our aerodynamic model and get the restoring pitching moment. And here are the results. So this is the restoring pitching moment, which should be negative for stability, positive for instability. The averaged contributions in blue are all destabilizing, which in agreement with what the community has been saying over the past 20 years, if you focus only on the averaged contributions, you get instability. But if you account for the vibrational effects within cycle variations, which was mainly neglected in the past, actually they are all stabilizing. Not only that, they are strong enough to outweigh the instability coming from the averaged body motion. So with that, we can confidently conclude that insect flight indeed enjoys vibrational stabilization. والحقيقه هنا النقطه اللي دايما very interesting ان يعني عظمه التصميم الالهي في ايه؟ ما هو في الانفيرتد pendulum I'm still paying the money for the vibration. I'm paying it. هنا this very natural motion is inevitably needed to create the lift force. So this very same motion gives you stability for free without feedback. Very smart design. We published it in Science Robotics. It made a bit of a splash. Science Robotics, actually, they invited people in the community to write a paper about it and like commentary about it. And also the Journal of Experimental Biology, they wrote about an article about it. منى الشاذلي كتر خيرها استضافتني. Other interviews, but this is just icing on the cake. It's the main point is the joy of the finding. All right, I'm gonna switch gears. Okay, as you can see, ما كناش هنقدر نعمل الشغل ده من غير theoretical models for aerodynamics. أنا محتاج at the end of the day a compact model أكتبه عشان أقدر أستخدمه أطبق عليه نظريات الداينامكس كنترول stability كل الكلام الجميل ده. So this is the traditional trade-off between accuracy and efficiency or computational complexity for fluid flows أو أي computational science, elasticity, whatever. For fluid in particular, we have the most accurate resolution in DNS direct numerical simulation, which I can never do on a real airplane, right? ومعظم الشغل من أول ال 60s, 70s, 80s and until this point مع ظهور الكمبيوترز. مع ظهور الكمبيوترز كان في like obsession. أنا أقدر أحل governing equations as is. So this is like crazy. فكل الناس شغالين almost في الحتة دي. Subgrid scale modeling for large area simulation, turbulence closure modeling for RANs, and like huge efforts here over the past 50 years or something. Very little effort is being done here because people think that it's actually saturated. It's right. But anyway, what I'm trying to say is this branch is super useful, but without having some models. Let it be empirical, let it be theoretical. Without true reduced order models, such a discovery would not have been possible. صح؟ فاحنا بنحاول motivated by this بنحاول push theory from below. So let's go together. الحقيقه انا كان المفروض اتكلم I promised in the abstract ان انا اتكلم على 3 حاجات. بس بما اني super excited about the third topic فانا I decided to neglect the second. Which is actually very interesting. I mean, the second was viscous extension of potential flow aerodynamics. So we're really proud of this contribution, بس أنا I'm super excited about the third. فأنا هركز على الثالثة. Okay, I apologize about that. So the new theory of lift. So let's go with the classical theory and see how it evolved over the years. I will start with Euler. So Euler يعني الحقيقة مش هقدر أديله حقه في الحتة بس anyway يعني أنا ليا محاضرة على النت على تاريخ الفلويد ميكانكس. You can go and see. I mean you can read many things, but لو عاوز كبسولة فالمحاضرة هتديك تاريخ الفلويد ميكانكس. Anyway لأن هو خلص الموضوع يعني هو خلص الموضوع هو من ساعة ما عمل الإيكويشنز 1755 لحد دلوقتي الإيكويشنز are exactly the same. على رأي هنري دوجاس في كتاب تاريخ الميكانيكا بيقول not a line has aged in that paper. Anyway تلاقي كمان الكلام ده في الكومنت بتاع لاجرانج على equation of motion بيقول equation of motion بتاعت اويلر for inviscid fluid مفيش friction. But the discovery of Euler قصده على equation of motion دي. The whole mechanics of fluids was reduced to a matter of analysis alone. هو قصده ان الموضوع خلص كميكانيكا. Force equal mass times acceleration done. It's now reduced to a matter of analysis. قصده mathematical analysis. هنحلها ازاي بالماثيماتكس؟ ازاي نعمل mathematical manipulation؟ Unfortunately, they are so difficult على equations of motion that up to the present, it has only been possible to succeed in very special cases. ده Lagrange late 1700 early 1800 تتكلم في 300 سنة. It's almost exactly the same status. Unfortunately دلوقتي هنقول نفس الكلام. Unfortunately the equations are so difficult مش عارفين نحلهم except for very special cases, probably the exact same special cases اللي Lagrange كان بيتكلم عنهم. Which is a bit shameful, frankly speaking. Anyway, D'Alembert بعدين قال والله يا جماعة لو UDX في DY WDZ is an exact differential meaning ان ده بيبقى D of some function يعني potential flow يعني ال velocity field is written as the gradient of a scalar function then الحاجات هتبقى اسهل بكتير. فلاجرانج jumped on it ومسك السبيشال كيس دي he derived the famous equation that we know under the name of Bernoulli equation, except it's really due to Lagrange. Bernoulli never wrote this kind of equation or even the steady version of it, but that's okay. But more importantly about this integral, so he showed that we can analytically integrate the equation of motion. I don't have a PDE anymore. This is an algebraic equation. أنا حليت كده خلاص. But more importantly, in the flow is governed by the Laplace equation, صح? Which is a linear equation admitting superposition. So we can decompose a complicated flow field into small, tiny, little elementary flows. Simply نجمع solution, superposition, which is for the first time. This is exactly what we teach in our undergrad, right? So fluid mechanics. So for the first time, it was done, to my knowledge, by Rankine. Use doublet distributions to get the flow around oval shapes. This is Rankine body. We teach it in our undergrad. And then really, the great paper of flow around a circular cylinder plus a vortex. This is the standard thing. So now we can get the flow over some nice shapes, huh? But not everything. So هنا في very important tool that was developed outside the mechanics community, in the mathematics community. Riemann mapping theory. أقدر map unit disk circular cylinder to whatever nice shape you like. So we're done now. معايا الفلو around circular cylinder, conformal mapping. I get the flow around any shape, let it be airfoil or any other thing. There is always but. So it's not complete. I can always add a vortex around the cylinder. And whatever the value of the vortex, arbitrary strength, 1, 1,000, 1 million, still the flow is always tangential to the surface. I'm satisfying the no penetration boundary condition. It's a legitimate solution. Ironically, this dictates the amount of generated lift force, which is the main or primary concern of an aerodynamicist. أنا كراجل aerodynamicist عايز إن الموضوع ده كله عايز lift or drag. فأنت بتقول لي الcirculation دي arbitrary، ممكن تاخد أي value. Okay, what about my lift? Your lift is simply rho u times this gamma. It's like ridiculous. Okay, what's the fix? The fix is the famous Kotta-Joukowski condition. صح؟ فجم قالوا والله يا جماعه انتوا بتتكلموا على airfoil with sharp trailing edge، اي sharp edge بتعمل singularity، let's remove the singularity. ده يديك condition تجيب بيها السيركوليشن وخلاص على كده. ف Kotta condition has many forms: smooth flow of the trailing edge, no flow around the trailing edge, no singularity at the trailing edge. And it's a brilliant condition. ليه؟ عشان it's like really a paradigm for inferring mathematical conditions from physical observation. This is the Prandtl flow visualization 1904. And this is the picture for the flow around an airfoil. And you can see here, look at this, the flow comes off smoothly off the trailing edge. There is no flow from the lower surface to the upper surface or vice versa. The Kotta condition is indeed, and it enabled the entire theory of lift. Right? But what if we don't have sharp edges? The entire theory immediately collapses. 2021, we don't have theoretical models to get the lift over a shape without sharp edge. Go and solve Navier-Stokes equations. What about unsteady flows? Well, we have an entire theory of unsteady aerodynamics. I'm actually teaching, I'm very interested in unsteady aerodynamics. I'm teaching a class regularly on unsteady aerodynamics. We have a whole theory starting with the work of Wagner, 1925, determining the lift response due to a step change in the angle of attack, all the way up to this paper in this very same year in the Journal of Fluid Mechanics, the most prestigious journal in fluid mechanics. All these efforts, they adopted the Kotta condition in their unsteady models, even though Martin Kotta never claimed that the condition will work on unsteady flows. In fact, we know for sure that it's not applicable. Look at this in the exact same catalog of pictures, Prandtl 1904. In the transient response, you can see that the flow rotates around the trailing edge from the lower surface to the upper surface. So we know already from more than a century that the Kotta condition is not applicable to unsteady flows, but there are no other alternatives. What do we know? What do we do? There are no other alternatives. All right. عشان الوقت I have to run. فأنا I already skipped the slide. So what is the reason behind this meager state of knowledge? Why is that? يعني ليه مش عندنا المشكلة دي في ستوكس فلو؟ يعني أنا عندي Navier-Stokes. I can go all the way to this end of the spectrum, taking the limit as Reynolds number goes to 0, or here Reynolds number goes to infinity. I have Euler and potential flow. ليه عندي المشكلة دي هنا وهنا لأ؟ لما تحطهم كده قدام بعض you immediately realize what's the main issue. This is Navier-Stokes, which is simply force equal mass times acceleration. This is incompressible, فأنا I'm taking the mass density يعني ب1. But this is force equal mass times acceleration, dynamics. Stokes flow, we simply ignore one term in the limit, but we still solve the dynamics, force equal mass times acceleration. In potential flow, what do we solve? We solve the Laplacian in the velocity potential. This is not dynamics. This comes from continuity, which is a kinematical constraint. It's divergence free, and here curl free. So just kinematics, there is no relation whatsoever between this and that. This is pure kinematics. And after you get your flow field, you go and substitute in Bernoulli's equation to get the pressure. So when you get the flow field, there is no link whatsoever to the dynamics. You don't feel the dynamics. So it's fair to expect that it's not complete, and you need a closure condition. So potential flow is purely kinematics. There is no dynamics whatsoever. Which means if we are to derive a closure condition for potential flow, because remember, quota condition is not derived from first principle. It's not derived. It's just singularity removal. If we are to derive a closure condition for potential flow, it must come from dynamics, dynamical consideration, something like force equal mass times acceleration. The challenge is ازاي اقدر اكتب force equal mass times acceleration and compress it to focus on one variable only, gamma. انا مش عايز حاجه غير gamma. This is the challenge. ازاي اكتب force equal mass times acceleration for a variable like gamma? This is the challenge. All right, so let's see. Let's go and review something about dynamics itself. Dynamics, we do dynamics in one of two main ways, right? Either Newtonian or Lagrangian analytical mechanics. Let's have a simple example. I have 100 particles in the plane. So each particle has 2 degrees of freedom. فعندي 200 degrees of freedom, x's, y's all together, but they are not all free. They are rigidly connected. بحيث في الآخر أنا عندي 3 degrees of freedom بس. If I have Q1 up to Q3, I can recover the x and y's of all the particles through the constraints. Okay. فأنا عندي 3 degrees of freedom. Okay. How do you solve this problem using Newtonian mechanics? The very first step, draw a free body diagram, right? You have to isolate each particle. And when you isolate the particle, all the forces show up. The applied forces, Fi, and what we call constrained forces. The constrained forces whose sole role is to maintain the constraint. They don't drive the motion. They are workless, actually. But this is the way Newtonian mechanics works. You have to account for these constrained forces. By constrained force, I mean if a particle is moving along a surface, there is a normal force that maintains this constraint, right? By definition, this normal force is always normal to the motion. It's gonna never drive the motion, but it's necessary. If you isolate the particle, you have to account for it, right? And they are unknowns. So how many equations you have at the end of the day? Well, we write mass times acceleration equal all forces for the 100 particles times 2 degrees of freedom in the plane, like 200, plus the 197 force, and they are unknowns. I mean, I don't want anything of them, yes, but you have to account for them. This is the Newtonian way, right? Projecting this on fluid mechanics, it implies that we isolate each particle and write down the equation of motion for each particle individually, and we have infinitely many of those. So at the end of the day, we get a PDE, partial differential equation, right? So this is the Newtonian way. Okay, good. What about the other way? The other way is common in analytical mechanics, but it's not common in fluid mechanics. The other way is very beautiful. And I'm going to quote Feynman, the famous Nobel laureate and famous physicist. Feynman كان بيدي ليكتشر بعد ما خد نوبل برايز، وافتكر وهو بيدي الليكتشر افتكر he recalled موقف ليه مع مدرس الفيزياء بتاعه مستر بيدر. فايمان كان دايما يعني هي elevates مستر بيدر ودايما بيتكلم عليه كويس وبتاع. فايمان في الهاي سكول كان مخلص اساسا كل الفيزياء والماثماتكس والكلام ده كله، قاعد very bored from classes، فقعد ملان خلاص ما فيش حاجه تثير شغفه يعني. فمستر بيدر قال له ايه؟ ريتشارد come I will show you something interesting. فبعدين جو بقى fast forward now هو بيدي الليكتشر بيقول بيحكي الحكايه دي وبيقول قال لي Richard, come, I'll show you something interesting. Then he told me about something which I found absolutely fascinating and have since then always found fascinating. Every time the subject comes up, I work on it. In fact, when I began to prepare for this lecture, I found myself making more analyses on the thing. And instead of worrying about the lecture, I got involved in a new problem. This thing is the principle of least action. الموضوع principle of least action is very famous. كل الموضوع ان انت عندك equivalent view to how things move. لما انا برمي ديت كده it moves according force equal mass times acceleration, but an equivalent view it moves while minimizing a certain magic quantity. فلو عندي tree leaf falling, an orbiting satellite, a hard bombing, they all move to minimize a certain magic quantity. It's like nature stores house. Nature is minimizing this quantity. فالquantity دي اللي هي الاكشن. فبالتالي if we view the dynamics from this perspective, I don't care about all these forces. Actually, you're gonna ignore the constraint forces, accept the constraints, simply write my action in terms of these variables only. In general, the action is in function of the motion, but we just from the beginning said that all the motion is represented by these 3 degrees of freedom. So my action is function of this. Now my action is minimum. Go and minimize it with respect to these guys. Partial A, partial Q1, Q2, Q3, zeros, 3 equations directly focusing on the dynamics of the Q's only without worrying about the entire 200 degrees of freedom and the unknown constraints. Beautiful approach. I mean, if you solve a complicated mechanics problem, of course, using Lagrangian is much easier if it's a complicated problem. So projecting this on our fluid mechanics aerodynamics, we are happy with the representation of the flow field in terms of gamma. If God gives us gamma, we're fine. So all what we need is to how to project dynamics to get the dynamics of one variable, gamma. So simply, this is very suitable formulation. Just go and formulate your action in terms of gamma, minimize it with respect to gamma, you're done. You get an equation, one unknown, we're done. And I have to emphasize that these are equivalent. I mean, in any mechanics class, we solve problem using Newtonian and using Lagrangian, we get the exact same set of equations. So the principle of least action has the same truth, the same status of a first principle. So conclusion. احنا قلنا ان if I want to get a closure condition for potential flow, it must come from dynamics. And we have 2 ways of dynamics. It is obvious now ان انا البرانش ده is much more suitable to do this job. When you say this, so the closure condition better comes from a variational principle for fluid mechanics. لما تقول الكلام ده fluid mechanicians بيتخنقوا. ازاي يعني؟ ليه؟ لأن fluid mechanicians the variational principle has been there for a while. This is a paper 1666, 88. I mean, there are many papers about Hamilton's principle of least action for fluids. They have almost never been useful for fluid mechanicians. Why? Because Hamilton's principle is for only conservative forces. So it cannot account for the viscous forces, which to fluid mechanicians, they're like, I mean, they are obsessed with viscosity, right? It's the origin of everything. So this formulation cannot account for one of the most important forces or physical effects for fluid mechanicians. So they don't prefer it. And in fact, this situation is exacerbated even more when you look at this. Okay, we have the velocity field. Like I said, we can formulate it function of gamma, right? If I have gamma, I can just write the velocity field everywhere. Go and form your action, the integral of the kinetic energy in the field. So this is function of gamma, and the x we integrate over x, so it's just a function of gamma now. So give me a gamma, I give you an action, minimize this action with respect to gamma, you get zero left. So it's extremely disturbing because it almost destroys the whole thesis, the whole proposal, right? Not only that, it actually matches the accepted wisdom in the community. Actually, أنا قدمت البروبوزل ده، أنا بحارب في الحوار ده بقالي مثلا 5 سنين. قدمت البروبوزل ده من 3-4 سنين كده، وده كان رد واحد من الريفيورز. بيقول it's worth remembering that the Kotta condition serves as a physically motivated determinant of the unique solution among an infinitely possible choices for implicit flow about a body in the plane. Fine. Look at this. It's a low order form of an essentially viscous constraint. بيتكلم على Kotta condition. The Kotta condition to any fluid mechanician is just a manifestation of viscous effects. فبيقول طبعا it's not clear to me that removing this constraint, low viscous constraint, and using instead the principle of least action to obtain a unique solution is physically relevant. وعنده حق، انا مجربها بنفسي طلع زيرو. Not only that, here is a PhD dissertation at Caltech in 1959, and here is the acknowledgement. Actually, the gentleman was acknowledging great people like Feynman himself and Liebman and Roshko. كان بيعمل ايه؟ كانوا برضو they are interested in this problem. يقولوا يعني فعلا Kotta condition is a viscous constraint، فعلا lift. لان if you ask any fluid mechanician where lift comes from, well, lift is due to vorticity in the boundary layer. Vorticity in the boundary layer is a viscous process. The Kotta condition is a viscous constraint. فكانوا عايزين يتاكدوا، فجابوا قال خلاص احنا هنعمل ايه؟ نجيب فلويد ما فيهوش فريكشن، ما فيهوش فيسكوستي، سوبر فلويد هيليوم 2، ونمشيه على فلات بليت واليبس وبتاع ونقيس الليفت. and they got zero lift. والراجل في الكونكلوجن بتاعه بيقول again the classical viscosity boundary condition at the trailing edge aka Kotta condition. Again he's acknowledging that the Kotta condition is a manifestation of viscous effects. It doesn't apply here لان ما عنديش viscous effects، ده super fluid. فكل ده made sense except that it's not correct, or to be nice it's not accurate. Let's see. Anyway, these are the conclusions so far. If I want to develop a true closure condition for potential flow, it must come from dynamical considerations. Some argument equivalent to force equal mass times acceleration. But it's challenging. We don't know how. And it seems that variational principles, let it be Hamilton's principle of least action or any other variational principle, at the end of the day, أنا عاوز حاجة تقلب لي المسألة لminimization problem. عشان minimize with respect to fewer number of variables. مش عايز أكتب equation of motion for the entire fluid لان في الاخر هريكفر نافير ستوكس، ما عملش حاجه. فدول التو كونكلوجنز اللي انا شايلهم على ظهري وماشي بيهم عمال ادور فين نعمل ايه يا جماعه. جالي ستودنت كودي جونزاليز كان قضى حبه وقت حلوين في الايرودينامكس اوف ريسنج كارز. فهو عمل رن لسيف دي يعني بعدد شعر راسه. countless he observed countless flow fields. وطبعا هو بيحل على عربيات، بيحل رانز، يعني مش ريرلي هيحل ال اس، والرانز مش ده. فدايما اي حد بيحل رانز بيبقى عنده كده ايه هيز اون سانيتي تشيك انتويشن، هو السولوشن ده شكله صح ولا شكله غلط، اقبله ولا ما اقبلوش. فالسانيتي تشيك بتاعه كان ايه؟ قال لك بص انا اي فيل لايك ان النورمال الفلو ما ينفعش يحود جامد. whenever you ask the flow field to turn with a large curvature it will not follow you، هتسيب السطح. فده السانيتي تشيك اللي جابه. فيقول لك دايما لما الاقي اروح احسب النورمال اكسلريشن فيلد والاقيه اعلى يعني عالي قوي، غالبا برفض السولوشن ده. Actually he even used it in design, like for example these two shapes they are very close but this shape has a discontinuity here in the curvature in the second derivative. فده it will demand a large curvature, large normal acceleration from the fluid, it will not follow. فده اوحش من ده في الديزاين. فالولد جاي اوريدي الجروب عندنا بالكونجكشر دي، غالبا there is a maximum normal acceleration ممكن يبقى فانكشن رينولدز نمبر وماخ نمبر. فهو ده الكونكلوجنز بتاعي لمده 4 سنين وهو جاي بالكونكلوجن دي. فقال طب خلاص انت بتحب المينيمايزيشن، تعالى مينيمايز انا النورمال اكسلريشن، ليتس سي وات وي جيت. فدي كلاسيكال ثيوري، بنكتب الفيلوسيتي فيلد لايك اور اندر ان ترمز اوف جاما، صح؟ let's have طبعا steady flow، فالاكسلريشن هي الكونفكتيف اكسلريشن بس، وليتس تيك ذا نورمال كومبوننت اوف ات. وعايزين ناخد absolute value او square doesn't matter much، وتعال integrate over the field. ده دلوقتي for any gamma I have a number here called k, and let's minimize k with respect to gamma. So let's plot k with respect to gamma. So this is at a given angle of attack we plot k versus gamma. This is for 0 angle of attack, 2 degrees, 4 degrees, 6, 8. At each angle of attack, there is a unique gamma that minimizes the curvature. And these gammas are simply the Kotta's values. which is an extremely mind-elating result. بس طبعا احنا في الاكاديميا مش هينفع نعديها كده، يا في theoretical basis يا by coincidence. فايه theoretical basis؟ minimization of curvature, minimization of normal acceleration. الحاجه الوحيده اللي جت في دماغي فقط من قراءه الهيستوري كان Gauss principle of least constraint. Actually, Gauss principle of least, if you open any modern book of analytical mechanics you like, you will not find it. You will never find it. It's only in history. So the great mathematician Gauss, he actually even wrote a paragraph. He didn't write an equation. He wrote a paragraph. And then people like Jacobi, they took that paragraph وعملوا له mathematical formulation. في ايه الموضوع؟ بيقول لك والله لو عندي set of particles mass times acceleration equal forces وعندي forces applied و forces constraints unknown. But the following quantity is minimum. We're searching for a minimization principle, okay? The following quantity is minimum. ايه quantity دي؟ تعال نبص عليها كده. دي الاكسلريشن، فدي الاكتوال موشن، صح؟ ودي دي الapplied force divided by the mass. So this is the intended motion, right? Actually, in the absence of constraint, they are exactly equal. مفيش constraints, apply force هاخد acceleration the same direction. خلاص. طيب لو في constraint, the actual motion will deviate from the intended motion, but this deviation is minimum. This is Gauss, just to one paragraph. Actually, you can see that this difference is actually R, right? The constraint. So actually, this is why it's called the least R, the least constraint, the principle of least constraint. One thing here, this F can be anything. It can be non-conservative. It can be anything, okay? طيب فحتى جاوس ليه تعليق حلو قوي. Remember جاوس هو اللي عمل least squares. ف it's clear ان هو هنا inspired from his method of least squares. Look at this. ده Gauss quoting from Gauss. It's quite remarkable that nature modifies free motions incompatible with the necessary constraints in the same way in which the calculating mathematician uses least squares to bring into agreement results which are based on quantities connect to each other by necessary relations. Nature بتعمل least squares. يعني ده اللي هو بيقوله يعني. Actually عشان اثبت لكم ان جاوس مش موجود، يعني روح دور عليه في اي حته، غالبا مش هتلاقيه موجود قوي في كتب الميكانيكا بالذات. هو باباستافريدس هير ده بالنسبه لي the most comprehensive book on analytical mechanics. 1200 pages حاجه كده، encyclopedia. وعنده كل التاريخ مع المودرن ستاف. فبيقول in most of the 20th century English literature Gauss principle has been barely tolerated as a clever but essentially useless academic curiosity when it was mentioned at all. واكشلي لو مسكت البرنسبل ده ورحت تحل بيه مسائل ميكانيكا عاديه بيندولم مثلا، it's like what's being what's going on. يعني فعلا يوزلس. يحل نيوتونيان يحل لاجرانجيان، ده واخد الاسوأ من الاثنين. But it just turns out ان هو very useful to us here. طيب one more thing, let's see how it's useful to us. One more thing, لو ما عنديش applied forces فالجسم free بس في constraint، فساعتها ماشي هنطبق جاوس مفيش مشكله، مفيش applied forces فانا بمينيمايز بس الاكسلريشن سكوير. اوكي. By the way, this quantity is called Appelian. ولما بتمينيمايز acceleration square in the absence of applied forces فenergy is conserved. This is equivalent to minimization of normal acceleration square. Again, this is called the Appelian. Now it's called Hertz principle of least constraint. Least curvature, I'm sorry. فتاني ده principle general, it's as generic as equivalent to Newton's equations of motion. لو ما عنديش applied forces it reduces down to Hertz principle of least curvature. بنمينيمايز الاكسلريشن سكوير it's called the Appelian or normal acceleration square. طيب تعالوا recall our equations of motion fluid mechanics. دي اويلر مفيش viscosity دلوقتي، ماشي؟ mass times acceleration, mass is unity واخدها incompressible فacceleration the left hand side equal forces. I need to classify the pressure force here. هل دي applied force ولا constrained force? And in order to apply Gauss, because when you apply Gauss you have to do this distinction. I mean when you do any analytical mechanics you have to do this distinction. فتعال نشوف البريشر فورس هي constrained force ولا applied force على fluid particle. This is a bit deep philosophical question. لان هو لو هي applied force فده هيبقى جاوس، لو مش applied force خلاص يبقى انا هريديوس داون لهرتز، right؟ طيب ده Euler equation of motion. You can easily show in one line if you have a U velocity field that satisfies continuity, second line, with no penetration boundary condition on the boundary, third line, then this equality is zero. What does this equality mean? It means that the pressure forces does not produce any work on the field. And again, it's rarely found in fluid mechanics books. Pressure forces are workless through divergence-free fields that are tangent to the surface, to the boundary. It is actually related to the very famous Helmholtz-Hodge decomposition. If you have any vector V, you can decompose it into two vectors. One of them is divergence-free, the other one is curl-free, so it's the gradient of a scalar function. And if this U is tangent to the boundary, so it's normal component 0 in the boundary, actually these two components are orthogonal in the sense of function, like here. So this equality holds not only with nabla P, nabla any F. Okay, so this is again related to the Helmholtz-Hodge decomposition. It's also related to Turin's standard projection in CFD. When you do standard projection, the very first step, he projects Navier-Stokes equation on the space of divergence-free fields, so the pressure force disappears because it doesn't contribute anything to the dynamics on that surface. Let me give you a pictorial image here. This is R3, okay? This is a blob of fluid. Okay. We have a map phi that maps your blob of fluid to its configuration after some time t. لو ده incompressible flow دي هتحصل لها deformation بس هيبقى نفس الفوليوم. تمام؟ ففاي طبعا هنا phi is volume preserving. Phi is a map, it's smooth function يعني. map يعني function. Phi smooth وليها smooth inverse. لما حاجه سموث وليها سموث انفرس الماثيماتيشن بيحبوا يعقدونا فيسموها ديفيومورفيزم. فلما اقول ديفيومورفيزم انا قصدي بس حاجه سموث وليها سموث انفرس. اوكي تمام. ففاي از ا ماب سموث ليها سموث انفرس وفوليوم بريزرفنج بتحافظ على الفوليوم عشان انا انكمبريسبل فلويد. تعال بقى نروح لفيكتيشس سبيس بتاع كل الديفيومورفيزمز. يعني الفانكشن دي فاي هنا نقطه. اوكي فده اتس فيكتيشس. دول كل الديفيومورفيزمز في منهم فوليوم بريزرفنج في لا. فده سطح بتاع الفوليوم بريزرفنج. فاكشلي الفيلوسيتي بتاعت فاي هتبقى تانجنت للسطح دوت لان بتحركك فقط على السطح ده. البريشر فورس هتبقى نورمال على السطح لان هي ما بتاثرش في اي حاجه في الداينامكس على السطح. وبالتالي الداينامكس بتاعت الانكمبريسبل فلو بتبقى على السطح ده فري ما فيش اي فورسز. ما هو في النافير ستوكس في بريشر وفيسكوستي. احنا شلنا الفيسكوستي بنتكلم على اويلر فما عنديش الا بريشر. فلو قلنا البريشر عمودي على السطح فاذا ما بيأثرش في اي حاجه along the surface. فالفلويد بيتحرك along the surface free. وزي ما احنا عارفين اي حاجه اي ميكانيكال سيستم بيتحرك فري بيتحرك على ايه؟ على ستريت لاين. وده كان الريزلت السيمينال ريزلت بتاعت ارنولد. motion of ideal fluid moves along geodesics straight lines in the space of volume preserving diffeomorphisms. كلام مجعلص جدا بس هو ده اللي قصده بيه في الاخر. At the end of the day, from all this discussion, it is really clear that the pressure is simply a constraint force. Its sole role is to maintain continuity فقط for incompressible fluids. فبالتالي تعال نطبق جاوس. جاوس دلوقتي هيريديوس لي هيرتز برنسبل اوف ليست كيرفتشر. اقدر امينيمايز الاكسيشن سكويرد او نورمال اكسيشن سكويرد. فبالتالي ده اويلر we just derive the variational analog of Euler. بدل ما تسولف البي دي اي دي بسي في دي روح minimize الاكسلريشن سكوير with respect to whatever variables you like subject to continuity and no penetration boundary condition. طبعا لو عملنا ده على المساله بتاعتنا بتاعت الايرفويل هقدر ببساطه دي قلنا الاس دي اسمها ابيليون minimize الابيليون. ادي الابيليون بتاعتي الاكسلريشن ستيدي كيس ستيدي هي الكونفكتيف اكسلريشن يو دوت نابلا يو هي فانكشن في جاما خدها سكوير كامل على الفيلد فالريزلت از جاست ا فانكشن اوف جاما. minimize it with respect to gamma. ده كده generalized Kotta condition ينفع في اي حاجه. وده اللي جاب الريزلت دي. خلي بالك كل ده كان ايه؟ كان inviscid. يعني الريزلت دي اللي هي again these are equivalent. This is Euler's equation of motion. This formulation is equivalent to Euler momentum conservation for inviscid fluids. For the case of a sharp edged airfoil ده بيريديوس للكوتا condition which means the Kotta condition is not a manifestation of viscous effects, but momentum conservation. Circulation and lift can be predicted from inviscid momentum considerations. For the first time, we can predict lift over cylindrical smooth shapes, not necessarily with sharp edges. Actually ممكن اعمل السبيكترم كله. تعال نزوم على التريلينج ايدج، اقدر اعمل ايرفول بالشارب تريلينج ايدج، ايرفول وذ سموث تريلينج ايدج. الاصفر ده اليبس البنفسجي، او الاخضر السلندر. ده ده كونتور بلوتس للاس الابيليون للاكسلريشن سكوير as a function of gamma, as a function of d the smoothing parameters. d is 0 sharp edged airfoil, d is 1 circular cylinder. ف d is 0 for any value of d. There is a unique value of gamma that minimizes the apillion, ودي true gamma. صح؟ ف d is 0 sharp edged airfoil، دي كوتا's value. d is 1 ما بيطلعليش انا لفت من circular cylinder، فطبعا المينيمم جاما هي 0. واكشلي مش السيركلر سيلندر بس، ده اي سيمتريك شيب، ودي ممكن نشوفها في الكويستشنز اللي انتوا تحبوا. انا خلصت. Insect flight indeed enjoys vibrational stabilization. I just presented a vibrational theory of lift via Hertz principle of least curvature. The Dakota condition is not a manifestation of viscous effects. Lift is mainly due to curvature. I'd like to thank funding NSF و Air Force, my students Ahmed Hassan, Cody Gonzalez, Nabil, Amir, Matasim, Muhammad Ali, and thank you so much. Questions? يا طبعا اللي انتوا تحبوه انا قاعد. تمام. اي اسئله؟ بليز. Insect flight, yeah. Sure. Insect flight. That real insect? This one? تمام. طيب واحده. الاكس اكسس، سوري about that. الاكس اكسس ده النمبر اوف سايكلز during the operation. فهو بيضرب الحشره، ودي هو actually I skipped lots of details in. Actually في موضوع كبير جدا we did not even ما قدرناش even نفسره، بس هذكره بالمره لان هو very interesting. البتاع ده كان دي لعبه جايبينها من الستور، بتضرب، فانا ما اقدرش اتحكم في القوه بتاعتها، يعني هي لعبه، فكانت بتضرب الحشره. احنا بنقيس الموشن بتاعت الحشره، فبقدر اعرف الديستربنس كانت قد ايه، مثلا كام راديانس بير سكند للبيتشنج انجلر فيلوسيتي. كانت بتبقى حوالي 4000 5000 ديجري بير سكند، والحشره في ده هيوج، والحشره بتريكفر within زي ما انت شايفه كده 3 سايكلز. السايكل هي بتتكلم في 30 هرتز، في حوالي مثلا 100 ملي سكند بتريكفر from 4000 degree per second. There is no man-made vehicle تقدر تعمل الكلام ده even the dynamically scaled version منها. بس ده مش الديسكفري بتاعتنا، دي احنا مش عارفين السورس، يعني دي actually an open question، مش عارف. فبالنسبه لي هنا على سؤالك، ده first cycle، ده second cycle، ده third cycle. انا بعد ما احسب الايرودايناميك مومنت طبعا هو بيتغير على السايكل، فباخد الافرج بتاعه، وده القيمه الافرج بتاعته نورماليزد، يعني نعمل نورماليزيشن. واحده دلوقتي انا باخد البادي موشن وعندي وينج فلابنج موشن، نقعد نعمل شويه ماثيماتيكال مانيبيوليشن كده، بس بغض النظر اللي بقدر اكستراكت الافكت بتاع البادي. لو انا هايزوليت، لو ما فيش اي فايبريشن، البادي موشن خدت ضربه، ما هو خلي بالك الحشره وهي واقفه اسيوم ما فيش ديستربنس خالص، الحشره واقفه، هي مش واقفه كومبليتلي ستيشنري، هي اون دي افريج كومبليتلي ستيشنري، بس هي واقفه تروح تيجي قدام، تطلع تنزل، عامله كده. ففي فاريشنز within ذا سايكل، وفي افريج، يعني مثلا بالنسبه لي الافريج هنا ايه؟ انه كله زيرو، تمام؟ فلما بتاخد ديستربنس وهترجع مثلا تراجكتوري، هتعمل كده وتروح قدام وترجع، في افريج تراجكتوري، واراوند الافريج ده في اوسيليشنز، تمام؟ فالتلد دي اللي عليها تلد دوت الويذن سايكل فاريشن، الاوسيليشنز اللي هم زيرو مين، وده الافريج. فwhen I account for the averaging, everything طبعا in the presence of wing flapping. When I account for the averaging, we pass these two added vectorially together خش على الايرودايناميك موديل. الايرودايناميك موديل كل اللي عاوزه الجيومتري وسبيد ريلاتيف تو دي امبيانت ويند، والامبيانت ويند زيرو. فانا عندي الموشن وعندي الجيومتري، اخش احسب الايرودايناميك مومنت، وبجيب بطرحه من الايرودايناميك مومنت اللي كان موجود قبل الديستربنس، اجيب الدلتا واعمل لها نورماليزيشن. خلاص برسم ديت، بجيب الافرج بتاعتها، تطلع رقم لكل سايكل، تطلع رقم. فدي للسايكل الاولانيه ده الاول، السايكل الثانيه ده الرقم، السايكل الثالثه ده الرقم. فلو خدت البار ده بيطلع لي البلو، لو خدت التيل دي بيطلع لي الاورنج، والاصفر ده التوتال. ده الريستورنج مومنت، فالمفروض يبقى نيجاتيف لو هو ستابلايزنج، يبقى بوزيتيف لو هو دي ستابلايزنج. فمعنى كده البلو كلهم بوزيتيف، يعني هم دي ستابلايزنج، ودول كانوا جايين من الافريجد، فده معناه ان الافريجد كونتريبيوشنز ار دي ستابلايزنج، وده بياكد كل الناس قالوه. بس هم كانوا بيهملوا الاورنج اللي هو كلهم ستابلايزنج، ومش ستابلايزنج بس، ده كمان ستابلايزنج وان هم they are strong enough to outweigh the instability here. Please.
كانت المشكله في المابنج بتاع الريمان ان الجاما بتاخد اربيتري فاليو.
صح.
هو في اخر المحاضره قلنا ان خلاص عرفنا المينيمم بتاع الاربيتري فاليو.
فهو ده حل المشكله دلوقتي، ان انا
ده حل المشكله.
يعني هجيب كان المشكله اجيب الجاما الحقيقيه منين؟ فكنت حللنا المشكله for the case of a sharp edged airfoil. طب لو مش عندي sharp edge، او لو عندي unsteady flow، هعمل ايه؟ فعايزين حاجه to come from first principles، فده اللي احنا قدرنا نعمله، ان derive something to come from first principle. هو الشغل ده still under review في PRL.
عملناه دلوقتي بقى في شارب ايدج ومش
اي حاجه مش فارقه. ما هو ليه الشغل كان confined؟ لان الاوبزرفيشن كان جايه من ايرفويل على شارب ايدج. فطب لو ما فيش شارب ايدج ما نعرفش، هو لازم حد يقعد يدرايف ات فروم فيرست برنسبلز. اللي تشالنج كان ازاي هدرايف فروم فيرست برنسبلز؟ ما هو انا عاوز داينامكس، الداينامكس بتديك نافير ستوكس، روح حل نافير ستوكس. ايوه، ما احنا بنقدر نحل نافير ستوكس، بس انا عايز حاجه ثيوريتيكال. فازاي ازاي بروجكت؟ دي مساله مشهوره، يعني مساله مشهوره في الريديوسد اوردر موديلنج. انا عندي نافير ستوكس بيعملها ديسكريتايزيشن، بتطلع مثلا مليونز ديجريز اوف فريدم. طيب ده الاوردر بتاع السيستم ده ايه؟ 4 مليون، 5 مليون، 10 مليون. عايز اديفلوب ريديوسد اوردر موديل، عايز بروجكت ده على 100 ستيت، يبقى سيستم اوردر 100 او اوردر 10. فدي مساله مشهوره، ريديوسد اوردر موديلنج، في برنسبل كومبوننت اناليسيس، بي او دي ودي ام دي، في علوم طالعه في الموضوع. بس هنا احنا بنعملها من الفاريشنال برنسبل ذات نفسه، من الداينامكس ذات نفسها، لان كل البرنسبل كومبوننت اناليسيس للاسف بتنجح في حاجات وتفشل في حاجات، تنجح في حاجات وتفشل في حاجات. فقصدي اقول حته بروجكشن بتاع infinite number of degrees of freedom زي بي دي ايز لسمول دايمنشنال ثينج، ده موجود في الدنيا. التشالنج هنا ان هو little bit more challenging. انا عاوز 1 degree of freedom، انا عايز بروجكت كل ده على جاما واحده بس. يعني فدي بتتعمل سهله جدا بالفاريشنال برنسبلز. هو لو انا عندي مفيش constraints، فبالتالي النمبر اوف x's and y's هم النمبر اوف degrees of freedom. there is no use for analytical mechanics. ما حدش يعمل analytical mechanics، روح استخدم نيوتن. لكن لو عندي constraints، فبالتالي انا كل اللي عاوزه بس الداينامكس بتاعت few variables، وهقدر منهم recover the entire thing. فعايز لو سمحت فوكس على الداينامكس بتاعت few variables by very definition. ده الاناليتيكال ميكانكس اللي بندرسه في الفيرست يير جراد سكول. هي المشكله كان الميسنج لينك ما بين الفلويدز كوميونتي والاناليتيكال ميكانكس، عشان اجين برضو الهيستوري ان هو، وايفن انا في الشغل بتاعي انا بقالي 4 سنين شغال في النقطه دي، مش عارف اطلع حاجه، لان دايما ايه اشهر فاريشنال برنسبل اوف ليست اكشن از نوت سوتبل، مش هو ده الصح. احنا محتاجين ده بالذات، هو ده جاوس، او يعني حاجه زي جاوس برنسبل اوف ليست كونسترينت. this is the right variational principle. Please. لا مش لازم، يعني واحده واحده. لو في فايبريشن هتاخد استابيليتي، اوكي، ولكن هل الاستابيليتي دي sufficient ان هي تكونكلود استابيليتي فور ذا انتاير سيستم ولا لا؟ دي بتختلف من حشره للتانيه. الحشرات الكبيره هتبقى عاده هتدي لها فول ستابيليتي. الحشرات الصغيره هتاخد ستابيليتي بس از نوت انف، محتاجه لسه تمبلوي فيدباك كنترول. Very good. This is a very good question. دايما احنا نفسنا نعمل التجربه دي بس ما كانش في وقت. ان هو انا ممكن البروبيلر ده ما انا بديله فولت وبديني ثراست بروبورشنال صح؟ اغير الار بي ام periodically بسرعه، اقلب بولاريتي وعشان اخلي الثراست فورس اوسيلاتوري ونشوف. فده دي احنا ما عملناهاش يعني ما جربناش بس كان نفسنا دايما نجربها.
كان يعني كان عندي اللي هو يعني كونستنت بس البروبيلر نفسها بتكون unbalanced.
ممكن this is another way of looking at it. Yeah.
انا بس عندي سؤال.
اتفضل يا دكتورنا.
البريشر في الانكمبريسبل فلويد انا دايما عليه كتير.
مثلا
هل له فيزيكال مينينج؟ هو لاجرانج مالتيبلاير.
exactly. هو exactly actually I can even derive it. مش عاوز لاجرانج مالتيبلاير؟
انا بقول في انا بقول
انا
عاوز اقول حاجه ثانيه.
قول طيب.
هل هو فيزيكالي له معنى؟
for incompressible fluids هو خليني let's put it this way. يعني عايز اقول الهدف منه او اصل وجود البريشر فورس في الانكمبريسبل فلويدز to maintain continuity. لو في two fluid particles جم شوت فلويد بارتكلز قربوا من بعض جامد جدا، فبالتالي الماس دنسيتي هنا هتزيد، هتفايوليت كونتينيوتي، يبدا البريشر يزيد ويرياكت. ولو الاثنين مشوا من بعض فتبدا الماس دنسيتي هنا هتقل، يبدا البريشر يقل از ا رياكشن. فهو بيشتغل دايما از ا رياكشن عشان تو مينتين كونتينيوتي فقط.
فيزيكالي تاني لو انا ادخل اللاب اقيس ايه؟
I see. This is your question. No, I mean that's physically هتقيسه بنفس البريشر سنسورز اللي موجوده. This is just a philosophical way to look at it. يعني I don't think ان هي هتغير في طريقه قياستنا. I don't think so.
يعني قصدي هل هو ده البريشر العادي فعلا ولا انا مش حاسس كده او حاسس ان هو صعب اعمل سيتويشن اصلا الاقي فيه البريشر اللي هو موجود في الانكمبريسبل كيس؟ صعب.
طبعا I totally agree. صح. صعب تجيب حاجه purely 100% incompressible يعني. even لو الماخ نمبر actually في سي اف دي سيموليشن معموله ماخ نمبر 0.1 و 0.2 وفيها شوكس وفيها compressibility effects.
قصدي ممكن هو يبقى قصدي كونسيكونس رياضي لاسامبشن فيزيكالي كان غلط، اللي هو موضوع ان احنا فرضنا ان هو انكمبريسبل.
I would think so. I would think ان هو mathematical ramification لحاجه. I would think so. هو طبعا it needs like a deeper discussion بس يعني on the fly كده I would think so. Very good. Please.
دلوقتي انا بدرس الهاملتونيان واللاجرانج بتاعي بقالي 10 سنين كويس، ومقتنع بشده ان الجاوسيان برنسبل ده مش موجود خالص.
Yeah.
كل الكتب يعني، فمشكور ان انت ده قلته لنا. انا بس عايز واحد تبعت لي البرزنتيشن.
Of course. يا سلام.
النقطه الثانيه بس السؤال بقى ازاي يعني قدرت انك انت تتحرك من الحاجات دي اللي هي نظريه قوي لانك انت تطبقها في الهندسه؟
ده سؤال. This is a very good question actually. This is a very good question. لأن هو الحقيقة أنا
صعب قوي بس يعني تيجي كده بس كومنتين ثلاثه يعني.
Yeah.
انا محتاج البرزنتيشن عشان اشوف تكست نص بس لو انت تحب تتكلم زياده.
هو مش هتكلم كتير. انا كل اللي عاوز اقوله ان انا رايح وانا I have a problem in mind frankly speaking. يعني انا في الاساس انا برضو بحب اشتغل فلايت ميكانكس. فانا هنا فعلا انا بحب اشتغل فلايت ميكانكس، فانا عاوز موديل بسيط عشان اقدر اروح اعمل بقى شغل الداينامكس كنترول بتاعي. انا actually I did not grow up as a fluid mechanician. انا grow up as a dynamics and control person. والPhD كانت dynamics and control. فانا عاوز حاجه بس satisfy my needs. فانا فعلا رايح وفي very specific need in my mind. بس للاسف الحل بتاعها مش موجود، فاحنا قعدنا نعافر شويه هنا. يعني عايز اقول خلاصه الكلام انا رايح وفي very specific practical need in my mind. مش I was not wondering كده وطبعا هي النقطه برضو، في نقطه حضرتك اثرتها مهمه جدا، ودي يمكن عشان الطلبه برضو، دي نقطه مهمه جدا حتى للطلبه. احنا في عصر دلوقتي موضوع التخصص ده يعني شديد جدا، يعني كل واحد اصلا حتى مش هيقول لك انا فلويد ميكانيشن، هو هيقول انا بتاع ايه، يعني هل انا كومبيوتيشنال فلويد ميكانكس ولا انا اكسبيرمنتال فلويد ميكانكس ولا انا ثيوريتيكال فلويد ميكانكس. فالتخصص بقى فضلا عن ان انا بقى بتاع فلويد ميكانكس ومعايا مثلا اناليتيكال ميكانكس، يعني انا I would think and there is no offense، I mean احنا كلنا في نفس البوت صح. I really believe in tools بتاعت الاناليتيكال ميكانكس whether it's principle fleeced action، جاوس principle، سيبك من جاوس principle عشان هو فعلا مش موجود، whether it's principle fleeced action whether it's even principle of virtual power، كل البرنسبلز بتاعت الاناليتيكال ميكانكس I would believe ان هي pure fluid mechanicians they would not be very familiar اللي هو يعني شاربها جدا. again there is no offense، التانيين برضو مش هيبقوا شاربين الفلويد ميكانكس يعني عادي، بس ده عشان العصر اللي احنا فيه، وده بيبان جدا في البي اتش دي بروجرامز، وبيبان جدا في الجيل الجديد من الدكاتره اللي هم زملائي هناك، اللي هو انا عاوز بابليكيشنز عاوز بابليكيشنز عاوز بابليكيشنز اي دونت كير الطالب يتعلم ولا لا، فانا مش عاوز الطالب اساسا يروح ياخد كورسات كتيره ويوسع الباك جراوند بتاعته. ففي مشكله اوريدي في الساينتفك كوميونتي حاجه زي كده، وات ايفر هي هتعمل امباكت ولا لا it doesn't matter at the end of the day، بس حاجه زي كده مش هينفع تتعمل الا بالتو اكسبرتيز دول سايمالتينيوسلي. وطبعا بره بيعوضوها بان هو يجيب واحد بتاع ده واحد بتاع ده يقعدهم مع بعض، بس مش مش دايما هو ده اللي بينجح. كل الاسامي اللي انا ذكرتها دي، كل الاسامي دي ما فيش واحد فيهم كان بيقول انا فلويد ميكانيشن، كل دول بتوع حاجات اكشلي. جاوس بالذات، جاوس دوت كان راجل بيور ماثيماتيشن، ما فيش حد فيهم بيقول انا بتاع حاجه يعني. فانا ما اعرفش ليه فجاه بدات الموضوع يبقى بالشكل ده. بس شكرا، هو يعني سؤال في محله يعني.
هل في عندنا اي سؤال او تعليق؟ شكرا جدا دكتور هيثم، شكرا لكم الحضور، ان شاء الله. بس في حاجات بسيطه هنا كده
مش عارف هل في حد عنده سؤال على الاونلاين؟
انا بعت لهم يا دكتور.
تمام، شكرا جزيلا. شكرا، تسلم. شكرا دكتور عمرو، متشكر جدا للانفيتيشن.
والله
ربنا يخليك يا دكتور.
بس الاول